alaikum wa rahmatullahi wa barakatuh. Welcome everyone back to session 2 of lecture 2 of ITDR1103. We will continue speaking about logic, and in this session we will introduce the logical equivalence and tautology, implications, converse, contrapositive, arguments in logic, and its validity. Now, if you didn't see the session 1, please you can go back to and check the session 1 because it has all the foundation information that we need in order to proceed in this session. So in last session, we already discussed about what do we mean by logically equivalent. And we say that if I have two logical expression and they have the same truth value within the combination of possibilities, we say that this is logically equivalent to this. So logical expression 1 and the logical expression 2. In order to say that they are logically equivalent, we need to mention that they have the same truth value within the same condition. Tautology is the logical expression that is always true. So this is a concept and this is the other concept. It was discussed in the last session. Now, if we have both a logical expression that they are logically equivalent and they are always having the same truth value, which is tautology, we are replacing the 3-line equal to this symbol. It's something like F and only F. So another way of saying that A and B are logically equivalent is to say that A and B are tautology. Implication. Implication, as we discussed in the beginning of this session or of last session, is the F then connective. It's also known as implies. So it's written as this notation and it can be read as FP then Q or P implies Q. All right. Now this expression called implication, which is FP then Q. Then if we just change the places of the reason and the conclusion, we call this as a converse. So the converse of FP then Q is FQ then P. And then we've got another vocab here, which is contrapositive, where we have the converse with not and not. So if not Q, then not P. Let's see this example here in order to understand the converse and the contrapositive. We have this implication, which is if I am in Salalah, then I am in Oman. Now the converse of this implication is changing the places of conclusion and the reason. So here we've got if I am in Oman, then I am in Salalah. Now the contrapositive is having the same converse, but we need just to have as negation of the preposition. So if I am not in Oman, then I am not in Salalah. So in this example, the original preposition is true. Its converse is false and its contrapositive is true. Let's summarize the converse, implication, and contrapositive in truth table. So we'll create a truth table that has two prepositions, which they are P and Q. Then we will find the implication. Then we will see the converse and the contrapositive. All right. Now, if we got two prepositions, then we are expecting to have 4 rows. They are true, true, false, false. And here we've got true, false, true, and false. Now we say that F then will be false if I got the first preposition true, then false. Otherwise, it is true. The converse is the positive, the opposite. So we'll see first at the Q, then P. And here we've got true. If true, then true is true. If false, then true is true. If true, then false is false. If false, then false is true. Now we'll have not Q, which is false, true, false, true. And here we've got not P, which they are false, false, true, true. Now, if not Q, then not P will have. If not F, then if F, then F is F. True, then false is, here we've got true. True, false, 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 true, 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 true. Now from here we can see that the implication is logically equivalent to the contrapositive. That's why implication here, implication, which is the original preposition, is true, and the contrapositive is true, while the converse has a false meaning. That's why implication and contrapositive are logically equivalent. So the truth table shows that column 3 and 7, which is implication and its contrapositive, are logically equivalent, where the implication and the converse are not logically equivalent. And we saw this at Salala and Oman example. All right, we've got something else in logic called arguments. The argument consists of some premises and a conclusion, which is supposed to be a consequence of the premises. We've already saw this word, and we knew that premises is something like reason or a condition. Conclusion is a result. So conclusion is the consequence of the premises, the result of the condition. Argument can be represented as the logical equivalent, as you can see here, P1 and P2, then Q. Now P1, P2, Q are logical expression. All right, now here is the premises, the condition, and here we've got the conclusion. The validity of an argument is if argument is valid, then the conclusion should be true whenever all premises are true. This condition, if met in an argument, then we can say that this argument is valid. The premises is true, the conclusion is true. So P1 and P2 is true, then Q must be true. All right, let's test this argument here. We have got FP then Q and not P, F then not Q. Then we need to find, is this is this argument tautology or not? So we will need to build a truth table, starting with the prepositions that we've got. So we've got 2 means 4 rows. True, true, false, false, true, false, true, false. The first premise is FP then Q. The first one here, this is P1, and here we've got P2, and this is Q. All right, so P1, if P then Q, we knew that true, if true, then true is true. If true, then false is false. If false, then true is true. If false, then false is false. P2 is not P, which is false, false, true, true. Now, P1 and P2, which is if P1, then Q, and not P, is equal to true and false, false, false and false, false, true and true, true, true and true, true. Q is not Q, so here we've got false, true, false, true. Now the full argument is if P1 and P2, then Q. So we will look at here, if here, then here. So if false, then false is true. If false, then true is true. If true, then false is false. If true, then true is true. Now, in order to check the validity of this argument, we need first to see for all P1 and P2 true, we should have the argument here true. As what is mentioned here, if P1 and P2 is true, then Q must be true. So we'll check here and check here. False true, it's okay. False true, it's okay. Here we've got this true, and here we've got false, which means that the argument is not valid because I have true as the premises while in conclusion is false. This is one. Two, we have the question that is this argument tautology or not? So if we look here, you will find that all the truth value of the final argument is true, 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 while I got here false. So also the argument is not tautology. So what can we conclude from the truth table? That the argument P1 and P2 then Q is not always true, which is not tautology, and the original argument is not valid. And we saw this in row 3 because the premises of the argument were satisfied while the conclusion was not satisfied. Let's move to the last part of our session today, which is laws of logic. In the previous slide, we come across those two logical expressions, which is Q and P or not Q, and P and Q. And we saw that those two expressions are logically equivalent. All right? So from here, you can see that some complicated expression can be replaced by a simpler expression without affecting the truth value. How we can do so? We can use laws of logic to simplify the logical expression. And what we did earlier, we used the truth table to just to show that this complicated expression is logically equivalent to that. All right? Let's see the laws of logic that we've got, and we will see how we can use them. So the first three laws of logic works with if and not. Equivalence, where if we got the if and only if, this is equal to if and if. Implication, if we got if, then this is logically equivalent to not P or Q. Double negation is equal to the preposition itself. And then if you remember, those laws are pretty similar to the laws of sets. So here we got commutative, associative, distributive, De Morgan's law, identity, annihilation, inverse, and absorption. Now laws of logic, we've got laws of logic not to memorize it, but to use it. So as much as we use, we will get familiar to it and we will know when to use what. So when we have a question under laws of logic, first thing we need to do is we remove the if statements, if and only if, and implication. All right? Then we can use the remaining laws involved and or not. Of course, the double negation law can be used a lot. So first thing you do is you will have to get remove the if connectives. If and only if then. All right. Let's say this example here. We will have to use laws of logic to simplify the following expression. So at the beginning of solving such questions, you will have to put the laws of logic in front of your eyes. But believe me, as much as you practice, you will get rid of it. You will know when to use what. Now let's see this expression here. First thing, we should look at if and only if and if then. And as you can see, we don't have any here. So what can we use? We can use, because we've got here and here or, we can use the commutative law. Sorry, the distributive law. However, we need first to convert it to the same of the distributive law shape. So first thing we need to do is we just change the place of Q. And in order to do so, we use the commutative law. It's really important you show which laws you use to solve or to move to the next step. Then we can use distributive law. In distributive law, we need to make sure that I've got two different connective. All right, so here we will got Q or P and Q or not Q. Now from here we can use that if I got the preposition and its or its negation, then using inverse law, this is equal to true. So here we'll got Q or P and true. Now using the identity law, yes, using the identity law, we knew that in AND, anything with true is equal to the thing itself. So here we've got Q or P. And here we reach the simplest form of the following expression using those laws. So why we didn't use the truth table? We actually used the truth table to determine the equivalence in the first place. We are not using it to show to simplify any logical expression. For example, if we got this question, I have this P and not Q, or Q, I need to verify whether this is equal to this. And here what we did, we simplified this expression to the one you can see here. So we can use the truth table to verify that those two expressions are logically equivalent. Now, how we can decide which law to use? There are actually no fixed rules to determine which law to use when simplifying expression. However, we can have like priorities. So the first priority is eliminating the if then and if and only if. Then we can use or we can try any law to help to simplify the expression. And yes, The process gets easier with practice. Let's see one more example here. And we try to simplify this expression. So first thing we will do before, first thing we will do is eliminating the if then. Now, by using implication law, we can have this expression as not P or Q, I'm sorry, it is not, and P. So by using implication law, we get that not P or not Q and P. Now we've got this negation on the outside. So in order to distribute this negation, we are using the De Morgan's law. Now in De Morgan's law, we will have, in order to distribute the negation, we will have got not P, change the connective, then we've got here not Q. And P. Now the double negation will equals the expression as not P will equal to P and not Q is equal to Q. And here we've got and P. So we can see that here the same connective and we've got same preposition. So in order to use the benefit of repeating the same preposition and same connective, we will use the commutative law. Commutative law will change the places. So here we've got P and P and Q. Now P and P using the idempotent is equal to P. So here we've got P and P is equal to P and Q. And here we reach the simplest form of the following expression. All right. Let's see this example. Here we've got two expressions and they are logically equivalent. Now the question asking us to use the truth table to verify whether they are logically equivalent or not. Because if we are using the, let's say, laws of logic, we will see that this is the implication law. So it's something like we prove the implication law. All right. So we start as usual. Here we've got two prepositions, which is P and Q. Two preposition means 4 rows. So the possibilities are true, true, false, false. Then Q is true, false, true, false. All right. Now we will find the logical expression, the first one, the truth value, and then we will go for the second one. So if P, then Q. If true, then true is equal to true. If true, then false is false. If false, then true is true. If false and false is also true. Now let's check the left-hand side of the expression here. So here we've got not P or Q. So first we need to find the not P. Not P is false, false, true, true. Then not P or Q. So we'll have to look at this column this column. So here we got false or true is true. False or false is false. True or true is true. True or false is true. So you can see here that this expression, which is FP then Q, is logically equivalent to not P or Q. So we can use the truth table to verify the logically equivalence of two expressions. It might consider as lengthy method, however, it always work. So laws of logic are usually shorter, but it's not easy at the beginning. However, this solves such questions and the other solve another type of questions. And here we reach the end of the logic topic in the lecture 2, where we introduced the logical equivalence and tautology. We saw the implication, converse, contrapositive, arguments in logic, and its validity, and then at the end we saw the laws of logic. Thank you for listening, and we'll see you inshallah in the next topic.